Section 1. Red Dwarf. Start with the most common star in existence. Red dwarfs make up roughly 3/4 of every star in the universe, and you can't see a single one with your naked eye. They're small, somewhere between 8 and 50% the mass of the Sun, and cool, sitting around 2,500 to 3,500 Kelvin. That's the temperature of a candle flame compared to the Sun's blowtorch. But being small is the ultimate cheat code. A red dwarf burns its hydrogen so slowly and stirs its fuel so thoroughly that it can keep going for over 1 trillion years. The universe is 13.8 billion years old. That means no red dwarf that has ever formed has had time to die. Not one. Every red dwarf ever born is still burning right now, and will still be burning long after the last big star in the sky has gone dark. Section 2. Orange Dwarf. Step up slightly and you get the orange dwarf. Around 60 to 80% the Sun's mass, 3,500 to 5,000 Kelvin. On paper, it's unremarkable. In practice, a lot of astronomers think this is where you'd actually want to live. Red dwarfs flare violently enough to strip the atmosphere off anything orbiting close. The Sun burns out in 10 billion years. Orange dwarfs split the difference, calm, stable, and burning steadily for 15 to 30 billion years. That's 2 to 3 times longer than the Sun will give us. If life needs time, this is the star that gives it away for free. Section 3. Yellow Dwarf. Which brings us to ours. The Sun is a yellow dwarf, 5 to 6,000 Kelvin, and despite the name, it isn't yellow. From space, it's white. The color you see at sunset is just our atmosphere scattering the blue light out of it before it reaches your eye. It's about 4.6 billion years old, which puts it almost exactly halfway through its life. And the second half doesn't end quietly. When the hydrogen in the core runs out, the Sun will swell into a red giant, swallow Mercury, swallow Venus, and either engulf the Earth or scorch it bare. Then it sheds its outer layers, and what's left of the core just sits there, glowing forever. Section 4. White Dwarf. That leftover core is a white dwarf, and it isn't really a star anymore. There's no fusion, nothing is being made. It's an ember the size of the Earth, carrying about as much mass as the Sun. A teaspoon of it would weigh around 5.5 tons, a small car in a spoon. And it does nothing but cool, slowly over billions of years, radiating away the last of the heat it was born with. The end state is a black dwarf, cold and completely dark. Except the universe isn't old enough for one to exist yet. Not a single black dwarf has ever formed. They're a prediction waiting on a clock that's barely started. Section 5. Blue Dwarf. Here's a stranger one. The blue dwarf doesn't exist anywhere. Not because we haven't looked, but because the universe is too young to have made one. The theory goes like this. When a red dwarf finally starts running low on hydrogen, it won't balloon into a red giant the way heavier stars do. It'll do the opposite. Heat up, brighten, and shift from red toward blue. It's a star type with a scheduled arrival date, and that date is trillions of years from now. Everything we know about them is math. Section 6. Brown Dwarf. Now go the other direction, down past the point where a star even works. Brown dwarfs formed the way stars form, out of collapsing clouds, but never gathered enough mass to ignite hydrogen fusion. They sit in the gap between the largest planets and the smallest stars, roughly 13 to 80 times the mass of Jupiter. They can fuse deuterium and sometimes lithium, but never the real thing, so they just cool and fade. Their surfaces run anywhere from about 300 to 2,500 Kelvin, which means the coldest ones are cooler than some planets. You could stand near one and feel less heat than a summer afternoon, and there may be nearly as many of them out there as there are actual stars. We simply can't see them. Section 7. Subdwarf. Then there are the old ones. Subdwarfs are dimmer than main sequence stars of the same type, and the reason is what they're missing. They formed before the universe had produced many heavy elements, so they're built almost purely from hydrogen and helium, the original ingredients. That makes their outer layers more transparent, which makes them look bluer and fainter than they should. Most of them drift out in the galactic halo, above and below the disk where everything else lives. They're relics, stars that were already ancient before the Sun existed. Section 8. Blue Giant. Now the temperature starts climbing. Blue giants burn hotter than 10,000 Kelvin and can shine tens of thousands of times brighter than the sun. And they pay for it. A star that massive tears through its fuel so fast that it lives only a few million years. Put that against a red dwarf's trillion. The brightest stars in the sky are also the most short-lived things in it. Many of the blue stars you can see tonight will be gone before our species is finished being a species. Section 9. Red giant. When a star like ours runs out of core hydrogen, it doesn't shut down. It starts burning hydrogen in a shell around the dead core instead, and that pushes the outer layers outward. Tens, sometimes hundreds of times the original radius. The surface cools as it expands, down to around 3,500 to 5,000 Kelvin, which is where the red color comes from. It's a strange kind of death. The star gets vastly bigger and vastly brighter while its surface gets colder. Ours does this in about 5 billion years. Section 10. Blue supergiant. Take a blue giant, let it exhaust its core and it doesn't cool down. It expands while staying furiously hot. Blue supergiants run from 10,000 up to 50,000 Kelvin, shine hundreds of thousands of times brighter than the sun, and carry 10 to 100 solar masses. They exist for maybe a few million years, and nearly all of them end the same way. The core gives out, gravity wins in less than a second, and the star detonates. Section 11. Red supergiant. By volume, nothing is bigger. Red supergiants form when the most massive stars expand outward, and some reach radii over 1,000 times the sun's. Betelgeuse is the famous one. Drop it where the sun is, and its surface would swallow Mercury, Venus, Earth, Mars, and keep going toward Jupiter. They're cool at the surface, 3,000 to 4,000 Kelvin, but the sheer area makes them blazingly luminous, and they're unstable, bloated, shedding material, sitting at the very end of the line. Every one of them is a supernova that hasn't happened yet. Section 12. Hypergiant. Above even that sit the hypergiants, the most luminous and most massive stars known, pouring out millions of times the sun's light and carrying over 100 solar masses. They come in blue, yellow, and red varieties, and every one of them is falling apart while you look at it, hemorrhaging mass through stellar winds violent enough to build entire nebulae around themselves. UY Scuti, a red hypergiant, has a radius somewhere around 1,700 times the sun's. These stars are astonishingly rare. They last only a few million years, and they end in catastrophe every time. Section 13. Wolf Riot. Some of them get stripped before they explode. A Wolf Riot star is a massive star that has blown its entire hydrogen envelope off into space, leaving the helium-burning core exposed to the vacuum. Surface temperatures run past 30,000 Kelvin and, in extreme cases, beyond 200,000. The winds coming off them move at up to 2,000 kilometers per second, fast enough to cross the Atlantic in under 3 seconds, carving glowing shells into the gas around them. You're not looking at a star with an atmosphere. You're looking at a naked stellar core burning in the open, days or millennia away from a supernova. Section 14. Neutron star. When that explosion happens, what it leaves behind is where physics starts breaking. A neutron star packs somewhere between 1.4 and 2 solar masses into a sphere about 20 kilometers across. A whole star compressed into the width of a city. A teaspoon of it would weigh roughly 6 billion tons. Electrons and protons have been crushed together into neutrons. There's no ordinary matter left. Some of them spin hundreds of times per second, and the gravity at the surface is around 2 billion times what you're standing in right now. Anything falling onto it wouldn't land. It would be smeared across the surface, atom by atom. Section 15. Pulsar. Some of those spinning corpses point at us. A pulsar is a neutron star firing beams of radiation out of its magnetic poles, and as it rotates, those beams sweep across space like a lighthouse. If Earth is in the path, we see a pulse. Regular, relentless, and in some cases more precise than an atomic clock. The first one was found in 1967 by Jocelyn Bell Burnell, and the signal was so impossibly regular that it was briefly labeled LGM1, Little Green Men, because nobody could immediately rule out that something had built it. Section 16. magnetar. Then there's the version with a magnetic field that shouldn't be possible. Magnetars are neutron stars carrying fields around 1,000 times stronger than a normal one, up to a quadrillion times Earth's. Bring one halfway to the moon and it would wipe every magnetic strip on the planet from there. In 2004, a magnetar called SGR-1806-2 let out a flare that in 1/10 of a second released more energy than the Sun puts out in 100,000 years. It disturbed Earth's ionosphere from 50,000 light-years away. Section 17. Black hole. And when the collapsing core is heavy enough, nothing stops it at all. A star above roughly 20 solar masses can end as a black hole, a region where gravity has won so completely that light itself can't climb out. The edge is the event horizon, and it isn't a surface, it's a one-way boundary. Stellar mass black holes run from about 5 to a few tens of solar masses. The supermassive ones sitting at the centers of galaxies reach millions or billions. We got our first direct image of one in 2019, the monster at the heart of M87, photographed by linking telescopes across the entire planet. Section 18. Quark star. There may be one more thing hiding between a neutron star and a black hole. The idea is that if you squeeze a neutron star hard enough, the neutrons themselves rupture, breaking down into the quarks they're made of, forming a state of matter denser than anything confirmed to exist. A quark star would be smaller and heavier than a neutron star, but somehow still hold itself up. In 2002, Chandra flagged 2 objects that looked too small to be neutron stars and too strange to be anything else. Nobody has confirmed it. They may be the densest things in the universe, short of a black hole, or they may not be there at all. That's the full range, from stars that will outlive the universe's current age 100 times over, down to objects so dense that matter itself stops working. Everything in the night sky is somewhere on that list, quietly running its clock down. Which one would you least want to live near? Tell me in the comments and subscribe if you want more of this.